Hello everyone. Hope you all watched lecture 1 where we covered definition, need of conformational analysis, terminologies used and factors influences the stability of a conformation. So in this lecture 2 we are going to explore conformations of some molecules and some additional features. Now let's start with the molecule ethane. In ethane we have a carbon-carbon single bond. The free rotation about this carbon-carbon single bond, generates infinite number of conformations. But here I have given only some important conformations which are having highest energy and the lowest energy possible. Okay. When the diagonal angle is 0 degree, we will get the eclipsed conformation, and when you carry out rotation, you will get staggered, eclipsed, like that. So this eclipsed conformation and staggered conformation repeats for every 60 degree dihedral angle. And I also told you in the last class, the eclipsed strain due to hydrogen atoms will be around 1 kilocalorie per mole. So in the eclipsed conformation of ethane, we have 3 pairs of eclipsed hydrogens. So the total energy is 3 kilocalorie per mole. In the staggered conformation, since there is no strain in the molecule, the energy of this molecule is assumed to be 0 or is considered as 0. With respect to this staggered conformation, the eclipsed conformation has 3 kilocalorie per mole of energy, potential energy greater compared to staggered conformation. Remember, the energy of the staggered conformation is not actually 0, but for comparison purpose we assume the energy of staggered conformation of ethane as 0. The potential energy diagram for ethane molecule is given here. When the dihedral angle is 0 degree, we get eclipsed conformation. For eclipsed conformation, the approximate energy is 3 kilocalorie per mole. So at 0 degree angle, we have the energy 3 kilocalorie per mole, and this corresponds to an eclipsed conformation. Then at 60 degree angle, we get the staggered conformation. For staggered conformation, energy is actually very low, but for comparison purpose we assume this value as 0. So for staggered conformation the energy is 0. Again at 120 degree we will get eclipsed conformation, then again staggered, again eclipsed, again staggered, like that it goes. Now I have told you already, the conformations having very low energy are actually called conformer. So here staggered conformation of ethane is actually called as conformer, whereas the eclipsed conformation having higher energy, which is not called as conformer. Okay, and the highest energy conformation called eclipsed conformation is actually called as a transition state. Okay, then right. So in ethane molecules, the staggered conformation potential energy is assumed to be 0, and for eclipsed conformation potential energy is 3 kilocalorie per mole per mole of energy greater compared to staggered. So the energy difference between these two is 3 kilocalorie per mole. This energy is nothing but the activation energy for the conversion of staggered form into eclipsed into again another staggered. Okay. Now we should know to what speed this free rotation occurs. Okay. Say for example at 298 Kelvin, right, we will calculate the rate constant. We know very well, according to Arrhenius equation, rate constant is a pre-exponential is equal to a pre-exponential factor into e power minus Ea by RT. And for most unimolecular process, the pre-exponential factor value is 10 power 13. This is actually a common value, so I am going to use this value as such. Then substitute the activation energy Ea, which is 3 kilocalorie per mole. For the conversion of calorie into joule, I'll multiply this by 4.184, and to convert kilojoule into joule, I'll multiply this by 1000. Then divide the value by R. R is 8.314 and temperature is 298 Kelvin. Okay. If you calculate, we'll get the answer as 6 into 10 to the power 10 second inverse. See, 6 into 10 power 10 is a very huge value. So that this actually indicates in 1 second 10 power 10 molecules of ethane get converted from one staggered form to another staggered form. See, 10 power 10 is not a simple number, it's a very huge number. So this rotation occurs in a very fast manner. Okay. So rotation about carbon-carbon single bond is extremely rapid. Then when we move from staggered form, one staggered form to another staggered form, the molecule has to cross the rotational energy barrier. So for the when you move from one staggered form to another staggered form, the molecule has to attain the transition state. Now the question is, the staggered form of ethane, the energy of the staggered form of ethane is 0, whereas the energy of the eclipsed form, also called transition state, is 3 kilocalorie per mole. Now the question is, where this 3 kilocalorie per mole of energy, okay, also called potential energy, is stored in the transition state. Where it is actually stored? It is actually stored in the form of torsional strain. It is actually stored in the form of torsional strain, right? As the hydrogen becomes eclipsed, a distortion of the CH bond occurs. As these bonds go back to their normal, length and angles in the staggered form, the energy required for the distortion is released to the ensemble of molecules. See, when the molecule move from eclipsed conformation to staggered conformation, the excess potential energy has to be released. Okay, the energy may be released to the surrounding molecules, or the energy may be transferred to a vibrational mode of the same molecule, right? And when molecule move from staggered form to another eclipsed form, okay, this vibrational energy again get converted into potential energy. So the transfer of energy back and forth between vibrational mode and torsional mode implies that the torsion is a vibration. Okay, so this is the point I like to give here. Torsion is also considered as a vibration because transfer of energy occur back and forth between the vibrational mode and the translational mode, torsional mode. Okay, so potential energy is stored in the transition state. Potential energy is stored in the form of torsional strain, and torsion is also considered as a vibration. Yeah, the next molecule is propane. Viewers, I am not going to discuss propane here. I am going to discuss butane directly. Based on butane, you try to calculate the rotation energy barrier for propane. We need not do exact calculations, which is not necessary. I have given some rough values for eclipse strain and all, right? Using those values, you try to get the rotation energy barrier for propane. Okay. So I will discuss directly the molecule butane. Yeah, N-butane has 4 carbon atoms, and there are 3 carbon-carbon single bonds. So free rotation is possible, right, in all the single bonds. But now the question is, which single bond we have to consider for conformational analysis? remember the single bond which will give the most stable conformer must be considered for the conformational analysis. Experimentally, it was found that the middle carbon-carbon single bond, okay, can produce the most stable conformation of butane. So we are going to consider that bond. Okay, and this is my my advice is that whenever molecule is given, okay, always focus on the middle carbon-carbon single bond, because in most of the molecules the middle carbon-carbon single bond, right, will generate the most stable conformer. Okay, then so I will take this single bond for conformational analysis. Okay, now I'll take this carbon as front carbon and this carbon as a rear carbon. So in the front carbon we have 2 hydrogen and 1 methyl group, and in the rear carbon also we have 2 hydrogen and 1 methyl group. Okay, so I'll start with the dihedral angle 0 degree. Now I am going to take dihedral angle for the 2 methyl groups alone. Okay, yeah, because that is the reference here, right? So I'll take methyl groups as reference, and based on the dihedral angle between the 2 methyl group, I am going to carry out the analysis, right? First start with the eclipsed, fully eclipsed conformation. What is meant by fully eclipsed? When methyl is eclipsed by methyl, hydrogen is eclipsed by hydrogen, right? We get fully eclipsed conformation. So when dihedral angle is 0 degree, okay, we will get the fully eclipsed conformation. Now I am going to carry out rotation about this carbon-carbon single bond. Okay, I am going to do rotation in clockwise, right? In this analysis, I am going to keep the rear carbon as such, and I am going to rotate only the front carbon. Okay, so when you rotate the front carbon, what will happen? This methyl group will come over here, and this hydrogen will go here, and this hydrogen will go here, correct? Okay, so and so we get this conformation where the dihedral angle between these 2 methyl group, is, okay, 60 degree, right? And I also told you that if 2 groups, right, if 2 groups have dihedral angle of 60 degree in a staggered conformation, right, we call that conformation as Gauss conformation. Then again a rotation in clockwise will produce partially eclipsed conformation. This is partially eclipsed conformation. In partially eclipsed conformation, methyl group is eclipsed by hydrogen. Okay, so it is called partially eclipsed conformation. Then again rotation in clockwise will produce a conformer where the 2 methyl groups are exactly opposite. So at a dihedral angle of 180 degree, the 2 methyl groups are exactly opposite, and this is the most stable conformer. Okay, remember, most stable staggered conformation is called anti-conformer. I repeat, most stable staggered conformation is called an anti-conformer. Then again rotation about clockwise in 60 degree will produce will give you 240 degree dihedral angle, where you will get the partially eclipsed conformation. Then further rotation will give another Gauss conformation. Then further rotation will give the original conformation. Are you able to follow? Now, so during this rotation from 0 degree to 360 degree, we get Gauss form into Gauss form 2 times, right? Then now I will show some energy analysis here. So in these conformations, right, from dihedral angle of 0 degree to 360 degree, we obtain these 4 major conformations. Okay, when the dihedral angle is 180 degree, we get this anti-conformation. In anti-conformation, the torsional strain or potential energy due to torsional strain is 0. Why? Because there is no torsional strain between methyl hydrogen having a dihedral angle of 60 degree. Okay. Then in the Gauss conformation, in the Gauss conformation, the dihedral angle between the two methyl group is 60 degree. When dihedral angle is 60 degree, the torsional strain between the two methyl group is roughly 0.9 kilocalorie per mole. So the potential energy of this conformer, also called Gauss conformer, is 0.9 kilocalorie per mole. Then in the partially eclipsed conformation, we have eclipse strain between methyl group and hydrogen, and the value of the eclipse strain between methyl and hydrogen is roughly 1.5. So this is one, like this we have two pairs, right? So 1.5 plus 1.5, 3, and the eclipse strain between two hydrogen is 1 kilocalorie, right? So this is the value of this pair. This eclipse strain is 1.5, and the value of this is another 1.5, okay, 1.5, and the value, the eclipse strain, the potential energy due to the eclipse strain between these two hydrogen is 1 kilocalorie per mole roughly, okay. So the total energy is 4 kilocalorie per mole for the partially eclipsed conformation, okay. Then for the fully eclipsed conformation, the eclipse strain between the two methyl group, you know very well this value is roughly 4 kilocalorie per mole, and eclipse strain between two hydrogen is 1 kilocalorie per mole. This is another 1 kilocalorie per mole. So this is 4, right? 4 kilocalorie, and this is 1 kilocalorie, this is another 1 kilocalorie. So total is 6 kilocalorie per mole, okay, of potential energy. Now if you observe the values, the anti-conformer, for anti-conformer the potential energy is assumed to be 0. With respect to the anti-conformer, the other conformers have little higher energy. So Gauss conformation has 0.9 kilocalorie potential energy greater compared to staggered, and this is 4 kilocalorie per mole greater compared to staggered, and this is 6 kilocalorie per mole, okay. Now we'll see the potential energy diagram for the carbon-carbon single bond rotation in butane. When the dihedral angle is 0 degree, we get the anti-conformer. When the dihedral angle is 0 degree, we get the anti-conformer, and for the anti-conformer, the potential energy was found to be 6 kilocalorie per mole. This is actually an approximate calculation, and the value given here is experimental. This is experimental value. Need not worry about that, because we need only we are going to compare the stabilities of these conformations. So you need not worry about the exact values, okay. So for anti-conformer, the energy is very high. Then at 60 degree, we will get a Gauss conformer. For Gauss conformer, the energy is 0.9 kilocalorie per mole. Then at 120 degree, we will get a partially eclipsed conformer. For this, the energy is roughly 4 kilocalorie per mole, and this value is exact. And for at 180 degree, we will get the anti-conformer, and anti-conformer is the most stable conformer, for which the potential energy is assumed to be 0, okay. Then again further rotation at an dihedral angle of 240 degree, we will get again another partially eclipsed conformation, then another Gauss conformation, then at 360 degree we get once again the original molecule, okay, called fully eclipsed conformation. Are you able to follow? So this potential energy diagram shows that the order of stability of conformations of N-butane is: anti-conformer is the most stable conformer, then the Gauss conformer, okay, anti-conformer is the most stable one, right, most stable one. I'll write here. So I'll give now, say I'll take this as A. A is the anti-conformer, and B is the Gauss conformer, and C is the partially eclipsed conformation, and D is the fully eclipsed conformation. So what is the stability order? Stability order, okay, stability order is this. Sorry. What is the stability order? Stability order is A, that is anti-conformer is most stable, then P, then C, right, then C, then D. Okay, this is how the stability varies in the case of N-butane. Okay, then this is a very important information in N-butane. You might have learned this term called enantiomers. What are enantiomers? Enantiomers or isomers or stereoisomers. They have object and mirror image relationship, but the two structures are not superimposable on one another. So I'll take a gauge conformation. This is gauge conformation when the dihedral angle is 60 degree. This is another gauge conformation where the dihedral angle is 300 degree. Now, if you compare the structures of these two, one is the mirror image of the other. So they have mirror image relationship, but they are non-superimposable on one another. So non-superimposable mirror images are actually called as enantiomers. But here one enantiomer can be converted into another enantiomer through carbon-carbon single bond rotation. Therefore, this type of enantiomers are called as conformational enantiomers. Right? These two are enantiomers and they are interconvertible. Interconvertible enantiomers are called conformational enantiomers. Okay? But the free rotation is so fast, therefore you will get these two always exist in 50-50 mixture. Therefore, you won't get any optical activity here. Okay, then suppose if I take a gauge form and I'll take an anti-conformation. If you compare these two structures, they do not have mirror image relationship. So these two conformations are called conformational diastereomers. You know very well, enantiomers have mirror image relationship but non-superimposable. Diastereomers, they do not have mirror image relationship, right? So diastereomers are stereoisomers. They do not have object and mirror image relationship at all. But here, this diastereomer can be converted into this. Therefore, these two are called conformational diastereomers. Okay, so this is very important. Keep this in mind. Then, so it is very clear that staggered conformation in general more stable than the eclipsed conformation. Okay, now I am going to show you some molecules, and I am going to show the method to identify the most stable conformers of these molecules, and this will be definitely help you to find the most stable conformer for other molecules. Okay, so okay, now we'll start with the molecule 2,3 dimethyl butane. In 2,3 dimethyl butane, there are a number of carbon-carbon single bonds available, right? We have totally 5 carbon-carbon single bond, but as I told you before, the middle one, right? The middle single bond is most preferred because that usually gives the most stable conformer. So I will take this carbon as front carbon. Okay, I will take this carbon as front carbon. This is my front carbon and this is my rear carbon. So in the front carbon, we have one hydrogen and 2 methyl group. Similarly, in the rear carbon also, we have one hydrogen and 2 methyl groups. Okay, so assume that this is front carbon, we have 2 methyl group and 1 hydrogen, and in the rear carbon also we have 2 methyl group and 1 hydrogen. And we know in general most stable conformations, right, are obtained, or the staggered conformations in general gives the most stable conformation. Okay, so here I have taken the two possible staggered conformations for 2,3 dimethyl butane. Now I am going to show you only how to identify the most stable conformer. Okay, and we know staggered conformers are more stable than eclipsed. So here I have taken two possible staggered conformations, right? Yeah, here see among the two which is most stable. Yeah, here we have a gauche, right? We have gauche interaction, right? Butane gauche interaction between these two methyl group, these two methyl group, and these two methyl groups. So we have 3 butane gauche interactions. So 3 into 0.9, it is roughly 2.7 kilocalorie per mole. Okay, 2.7. Okay, whereas here we have butane gauche interaction between these two methyl group, gauche interaction. Okay, when two methyl groups are separated with a dihedral angle 60 degree, the torsional strain between the two methyl group is roughly torsional strain will produce 0.9 kilocalorie per mole of potential energy to the molecule. Okay, so when two methyl group is in gauche, it will raise the potential energy by 0.9 kilocalorie per mole. So this is 0.9. Similarly, this is 0.9. 0.9 plus 0.9, it is 1.8. It's 1.8. So between these two, this isomer has less energy. Therefore, this is considered as the most stable conformer. Right? Among the two possible staggered conformations, this is the most stable conformer. Suppose instead of methyl group, if we have any other alkyl group, say ethyl or propyl like that, then geminal repulsion, right, plays an important role. Right? So I will discuss that type of question later. So keep this in your mind. In methyl group, geminal repulsion is not so dominant. Therefore, we are considering only the gauche interactions. Okay. So which is the most stable conformer? The second one. Then the next question: draw the most stable conformer of this molecule. Okay. Yeah. Now here we have a carbon-carbon single bond, and another carbon-carbon single bond here, and another carbon-carbon single bond, and we also have one more single bond here. Now we always prefer the middle one. So take this carbon-carbon single bond for conformational analysis. Now so I'll take this as the front carbon and this as the rear carbon. So front carbon has 2 hydrogen and a phenyl group with a methyl at the ortho position. Okay. Now what is the most stable conformer of this? We know in general staggered conformation is more stable. Okay. Now I'll show you. Yeah. So this is the molecule. For this molecule, what are the staggered conformations possible? Right. Now here, so in the front carbon we have 2 hydrogen. And we have a phenyl group with a methyl at the ortho position. Okay. Then in the rear carbon we have 2 hydrogen. The rear carbon we have 2 hydrogen and 1 methyl group. Okay. And this is one possible staggered conformation. This is another possible staggered conformation, and this is the this is another possible one. Okay. Now among the three, which is the most stable conformer? The most stable conformer is this, no doubt. Why? Because this group, right, which has this is actually benzene ring is planar, but this methyl group is tetrahedral. So when this methyl group is present nearby with nearby hydrogen, the interaction will be very, very less. Okay, therefore this staggered conformation is the most stable conformation. Okay, so this is the most stable conformation, right? Suppose if I take this as A, right, this as B, and this is C, right, then what is the stability order? Stability order is, I'll give here. So what is the stability order? stability, right? Stability order is this. C is most stable, right? Because the interactions are very less. Now 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 suppose if you consider these two structures, right? If you consider these two structures, see here the dihedral angle between this this phenyl group and this methyl group is 60 degree. Similarly, in the conformation B also, the dihedral angle between the phenyl group and the methyl group is 60 degree. So these two conformer supposed to have same energy, but if you assume that the structures are frozen structures, right? Frozen structure means this carbon-carbon single bond, if you assume this single bond does not undergo any rotation, right? Very clear. If this single bond and this single bond, if this two single bond does not undergo any rotation, then this structure remains as frozen structures. In the frozen structure, see the methyl group at the ortho position and this methyl groups are very close. Therefore, there will be van der Waals repulsion exist. Because of van der Waals repulsion, potential energy of this conformer will increase. Whereas in this conformer, that this methyl group and this methyl group are far away. So van der Waals repulsion is absent here. Therefore, among the two, this conformer has higher potential energy. Therefore, it is less stable. So among these two, B is more stable. Right? B is more stable than A. B is more stable than A. Okay, are you clear? Then the next question. Yeah, now we'll consider ethane 1,2 diol. This is the stability order. Okay, gauche is more stable than anti, partially eclipsed, fully eclipsed. Now the question is, why gauche is more stable than anti? What's the reason? The reason is, see, the reason is this. What is the reason? See, suppose instead of ethane 1,2 diol, I will take a general example where OH group is attached to one carbon and some X group is attached to the other carbon, adjacent carbon. Okay, if this X can be fluorine, OH, NH2, OCH3, ACHO, etc. Now, these are all the possible conformations, right? You know very well how to get all these conformations, right? Okay, due to by rotating about carbon-carbon single bond, you can generate all these conformations. Okay, now this is eclipsed conformation. This is staggered, eclipsed, staggered, eclipsed, staggered. In general, staggered conformations are more stable than eclipsed conformation. So here we have a staggered conformation here and another staggered conformation here. Okay, and these two are actually same, one and the same. Okay, because this is gauche, this is also gauche. So I'm going to consider only these two. Now the question is, among these two, which is more stable? See, in this conformer, the OH group and the X groups are exactly opposite. So it is an anti-conformer. Therefore, there is no interaction between this OH and this X. So in most people expect that this conformation must be the most stable conformation. But the answer is not that. The answer is this gauche conformer is more stable in this case. Why? Because there will be an intramolecular hydrogen bonding exists between this hydrogen and this halogen. Okay, see, so because of intramolecular hydrogen bonding, I told you in the factors influences stability of conformations. Intramolecular hydrogen bonding increases the stability of the molecule. So if you compare these two, right, this conformation is most stable one, right? This is most stable conformer. most stable, this is the most stable conformer. Okay, this one is the most stable conformer. Are you clear? Yeah. Yeah. So this is not only for ethylene glycol. You can take any molecule. Okay, in the place of X, you can put any of these groups, right? In all these groups, you will get Gauss conformation is as more stable over anti-conformation, right? Then the next question. Yeah, we'll discuss this question later. Now, I have another set of questions here. I have another set of questions. So this is question number 1. Draw the most stable conformer of succinic acid at pH 5 equal to 5 and pH equal to 10. pH equal to 5 means acidic medium. pH equal to 10 is basic medium. So in acidic medium, what will be the most stable conformer of succinic acid? And in basic medium, what will be the most stable conformer of succinic acid? Okay, yeah, we will discuss this question first. So this is succinic acid. Okay, I'll take this carbon for conformational analysis, right? Remember, in acidic medium, acid exists as such. So the succinic acid exists as a neutral molecule in acidic medium. Okay. Now, what are the possible staggered conformations for this? So this is the staggered conformation, which is called anti. And this is another staggered conformation called a Gauss conformation. Here, the dihedral angle between this acid group and this acid group is 180 degree, and in Gauss it is 60 degree. But among the two, which is more stable? Listen, here the two groups are far away. There is no interaction between these two groups. So people expect that this should be more stable. Okay, we expect this should be more stable compared to this. But in Gauss conformation, due to intramolecular hydrogen bonding, right, between this acid group and this acid group, okay, this conformation becomes more stable over anti. So among these two, Gauss is more stable over anti. What is the reason? The reason is intramolecular hydrogen bonding, right? Suppose if you go to pH 10, right, in pH 10 in basic medium, see, in basic medium, acid reacts with base forms salt. So in pH equal to 10, succinic acid exists as a salt. You know, remember salt will ionize, so that this anion, dianion exists in the solution. Okay. Now, for this dianion, we have two possible staggered conformations. This is anti-conformation and this one is Gauss. Okay. So this is anti-conformation. I'll just put A, and this is Gauss conformation G. But now, since these two carboxylate ion carry negative charge, okay, there will be repulsion. Okay, there will be repulsion exists because they have same charge. Okay, so because of repulsion, Gauss conformation, right, gains potential energy. Therefore, the stability of Gauss conformation become less, right? Whereas in anti-conformer, the two carboxylate ions, they are far away from each other. Therefore, the repulsion is minimum, and this anti-conformer is most stable conformer in pH equal to 10. So remember, in pH equal to 5, Gauss is more stable over anti, whereas in pH equal to 10, right, anti-conformer is more stable over Gauss. It's a very important, it's very nice question. So keep this in your mind. Okay, very easy also. Then, so in pH equal to 5, Gauss is more stable over anti. In pH equal to 10, anti is more stable over Gauss. Then the next question, draw the most stable conformer of this ion. okay, where chlorine is attached to one carbon and the NH3 plus ion is attached to the adjacent carbon. So with respect to this carbon-carbon single bond, right, we have only one carbon single bond here. So with respect to this carbon-carbon single bond, what will be the most stable conformer for this ion? Okay, yeah, we'll discuss that answer. So these are the two possible staggered conformation for that ion. Chlorine is attached to one carbon and NH3 plus attached to the rear carbon, adjacent carbon, right? And here the chlorine and NH3 plus are far away from each other with a dihedral angle of 180 degree. Okay, therefore repulsion between chlorine and NH3 plus is minimum here. So we expect that anti-conformer, suppose this is anti-conformer, so we expect that anti-conformer is supposed to be more stable. Okay, whereas see, this is actually gauche. In gauche conformation, chlorine and the NH3 plus are exist with a dihedral angle of 60 degree, right? And you know very well, chlorine is attached to carbon here. Since the electronegativity of chlorine is high, so chlorine gets partial negative charge, right? Now this chlorine has partial negative charge and the NH3 plus has positive charge. So between these two, since the charges are opposite, there will be an attraction. Okay, ion dipole attraction, I can say like that. Intramolecular ion are simply opposite charge attraction, right? Because of this attraction, right, gauche conformation becomes more stable over anti-conformation. So in this case, remember, gauche is more stable over anti. Gauche is more stable over anti. Are you able to follow this? Yeah. So in this case, gauche conformation is more stable over anti because of attraction, right? So this positive charge is attracting the partial negative charge of chlorine, right? Then what's the next question? Draw the most stable conformer of ethanol, right? See, in ethanol we have one carbon-carbon single bond, CH3. Okay, in ethanol, the conformation actually depends upon the rotation about carbon-oxygen single bond in ethanol. Okay, if the alcohol is a simple alcohol, say methanol or ethanol, right, then carbon-oxygen single bond, this rotation, this single bond rotation will give you the most stable conformer. Okay, what is that? See here, free rotation about carbon-carbon single bond does not provide you the most stable conformer. Okay, whereas the free rotation about carbon-oxygen single bond will give you the most stable conformer. So that's why I have taken this example. But you cannot take this for all molecules. Okay, yeah. Then now see, so this is ethanol. Now I am going to consider this carbon-oxygen single bond for conformational analysis, and these two are the two possible anti-conformer. Okay, I will take this as a rear carbon. This is the rear. I am going to take the carbon as a rear atom, and the oxygen is a front atom. Okay, front. So in oxygen we have one hydrogen, and there will be two lone pairs. Right? There are two lone pairs of electrons. Here one lone pair, here one lone pair, and like this. So there are two lone pairs, and lone pairs occupy the hybrid orbitals, right? So one lone pair occupy one hybrid orbital, and another lone pair occupy another hybrid orbital, right? Now we have two possible staggered conformations. Okay, where this methyl group is actually between the two lone pair. Here the methyl group is adjacent to one hydrogen, and this side we have a lone pair. Now among the two conformer, which is more stable one? Remember, according to Gauche effect, I have given already Gauche effect, right? I am going to give you another important meaning of Gauche effect. Listen, in Gauche effect, the lone pair does not occupy any space, or lone pair should be considered as an empty space. So So if you consider this as empty space, then this must be the most stable conformer. Are you able to follow? Because the bulky group is present between the two lone pairs. Since lone pairs are considered as empty space, right? Therefore, this conformation must be the most stable one. Whereas here this is also stable, right? But there will be a small interaction exists between this methyl and this hydrogen, right? This interaction is not so big, but if you compare these two, this must be the most stable one. Okay, are you clear? Then. So this is the most stable conformer. This is the most stable one. Okay, most stable conformer. Okay, I stop here. We'll continue the remaining questions by next class. Thank you.